Hello students and welcome to Chemistry B. I'm Ms. Slate and today we're going to talk about energy change in chemical reactions. So first off, if you take ethanol and ignite it, it will react with oxygen from the air and energy gets released in the form of heat and light. And obviously if you were to try and touch the flames, they would feel hot. This is the definition of an exothermic reaction, a process that releases heat energy. And typically, exothermic is symbolized by a negative change in heat energy, negative delta H. Again, because we use the negative to designate energy being released from a system. On the other hand, if you take ammonium nitrate and you dissolve it in water, you will see that the temperature decreases and the solution feels cold to the touch. That's because the solution is absorbing energy from its surroundings. This is the definition of an endothermic reaction. So an endothermic reaction is a process that absorbs heat energy. And it's symbolized with a positive delta H, or a positive energy value. Because again, positive energy value indicates energy being absorbed by the system. Now, we can actually calculate quantitative values for this change in energy. As usual, though, we got to start with a balanced chemical equation, and we're going to use the combustion of ethanol as our example. So what we find when we balance this is that our coefficient should be a 1, a 3, a 2, and a 3. And when we do this for the purposes of calculating our change in heat energy in a reaction, we need to write out the structural formulas for all the molecules, because we need to know all the individual bonds that get broken and formed in the reaction to calculate the energy. So in this case, we just wrote out the structural formula for all of the individual molecules in the reaction. So to break bonds requires energy to be absorbed, okay? So the system has to absorb energy in order to break all the bonds in the reactants. Forming bonds, on the other hand, releases energy. So the system needs to release energy every time it forms bonds in the products. So breaking bonds requires energy. Forming bonds releases energy. So to figure out the heat of the reaction, you're going to take the energy required to break all the bonds of the reactants and subtract the energy required to form all the bonds in the products. And so to do this, we use our table of bond enthalpies, and this should be right in your packet, and it'll also be given to you on the quiz. And you can see that every single different type of bond, including the difference between single, double, and triple bonds, is associated with a different enthalpy. And those enthalpies are given in units of kilojoules per mole. And we're going to use those to help us calculate the heat of reaction for the combustion of ethanol. So again, when we look at this, again, the heat of reaction is bonds broken minus bonds formed. So here we have 5 times CH, and that is because there are 1, 2, 3, 4, 5 carbon-hydrogen single bonds in the reactants. So we're going to need 5 times the enthalpy of a carbon-hydrogen bond plus a carbon-carbon single bond, because there's 1 carbon-carbon single bond, plus a carbon-oxygen single bond, because we have 1 carbon-oxygen single bond, plus the enthalpy for oxygen-hydrogen single bond, because there's also 1 oxygen-hydrogen single bond, plus 3 times an oxygen-oxygen double bond, because we have 3 of those representing the 3 oxygen molecules involved in the reaction. And so all of that gets added together, so that's why the brackets are around all that, because this is all of our bonds broken minus, again, all of our bonds formed. So there are 4 carbon-oxygen double bonds, 1, 2, 3, 4 in the products, and there are 6 hydrogen-oxygen single bonds, 1, 2, 3, 4, 5, 6. And so again, this is going to be the bond enthalpy of our bonds formed. So then we use the table of bond enthalpies, and we're going to substitute in the numbers for each of those bond types. So we end up with 5 times 414 kilojoules per mole plus 368 kilojoules per mole plus 352 kilojoules per mole plus 465 kilojoules per mole plus 3 times 498 kilojoules per mole, and that is the energy of our bonds broken, minus 4 times 532 kilojoules per mole plus 6 times 465 kilojoules per mole, and these are our bonds formed. When we are able to work all that out, we should get a heat of reaction equal to negative 169 kilojoules per mole. And it should make sense that this heat of reaction is negative, because we said the combustion of ethanol releases energy, so it is exothermic. Exothermic, releasing energy, is going to end up with a negative heat of reaction. Let's look at another example, the formation of ammonia. Again, as always, balance the chemical equation. Should be 3 hydrogen plus 1 nitrogen gives us 2 ammonia molecules. And again, just like before, once we have our balanced chemical equation, we're going to write out the structural formulas. So again, hydrogen, we've got 3 of them. So we drew out 3 of our hydrogen molecules. Nitrogen, the N2 molecule is a triple bond, so we've got 1 of those. And then our 2 ammonia molecules is nitrogen bonded to 3 hydrogens. Once again, heat of reaction is bonds broken minus bonds formed. We have 1, 2, 3 hydrogen-hydrogen single bonds that are going to be broken, so 3 times the hydrogen-hydrogen single bond. And we've got 1 nitrogen-nitrogen triple bond, so plus that bond enthalpy, minus, in the products, we have 6 nitrogen-hydrogen single bonds. So when we plug in our numbers for our bond enthalpies, we get 3 times 435 kilojoules per mole plus 950 kilojoules per mole minus 6 times 460 kilojoules per mole, which comes out to a heat of reaction of negative 505 kilojoules per mole. The fact that our heat of reaction came out to be negative tells us the formation of ammonia is an exothermic reaction. It's one that releases energy. And that is how we can calculate the heat of reaction for any problem. You got to have the balanced chemical equation. You got to write out your structural formula, figure out how many bonds of each type are being broken and formed, and then substitute in the bond enthalpies for each bond type from our table.